vede bene che so contro luce. Poi non sono andato dal parrucchiere, dal barbiere.
Live.
Allora, iniziamo?
Sì.
Okay, welcome. We have decided to proceed with we have 6 students that are going to graduate today, and then 3 in artificial intelligence and robotics, Faricelli, Faticoso, Roggiolani, and 3 in engineering computer science, Abruzzo, Trapasso, Trenta. And we have decided to proceed by first considering student in artificial intelligence and robotics, and then later the students that will graduate in engineering computer science. So we believe that we will start the second part in engineering computer science at 11:30. And so we are here, but this is to let you know in case you want to connect later. So 11:30, we will start with the second session of graduation. So now let's start immediately with the first student, Faricelli Simone, that I invite to share the screen and to start his presentation. Please.
Thank you, Professor. Is the stream visible?
Yes.
Okay, so I can start. Okay, my thesis is on an innovative deep learning solution for message analysis and classification applied to the field of customer care. I want to start this research by presenting and discussing a vertical analysis concerning all the components of Italian natural language processing and classification. This journey begins in the social language management, which is composed by 3 big parts that are morphology, syntax, and semantics. The morphology one contains parts like text cleaning, which we can see on the right with issues and example, normalization with stemming and lemmatization, and then tokenization, which means granularity of the characters or words. Okay, then we can move on to syntax and semantics. In this part, we can find the part of speech, dependency relation, name and entity recognition as additional information to our models. Then we can move on into the real NLP part, so the deep learning one. And we can decide which input to use for our model. We have basically 3 choices. Those are feature-based, word embeddings, and transformers. TF-EDF is the most widely known for the feature-based, and it gives us, like we can see in the example on the right, a value of the frequency of some terms. Whereas the word embedding instead maps the input into an n-dimensional space and transforms the words into vectors. Transformers instead are the new state-of-the-art mechanism, which is unlike word-to-vec or word embeddings, managed to overcome the issue of word contextualization. It does identifying which is the meaning of a specific word through the use of this attention mechanism that put the attention on specific words. Transfer learning is the concept at the base of the transformers model, and means that we can transfer the knowledge from one task or language model, in this case, to another. So we train a large corpus, we train a model on a large corpus like a dump of Wikipedia, and then we can move on to use that pre-trained model for fine-tuning on another task. About the classification models, instead we can find different models widely known, like CNN, RNN, LSTM, and BERT. We will see all of them, and we will compare the results in combination with LSTM and word embedding inputs. The BERT, which is the state of the art, is based obviously on the transfer learning. The way it is pre-trained is through self-supervised learning, which means that are generated 2 fake tasks named Masked Language Model and Next Sentence Prediction, in which in the first one, we mask randomly some words, and then we try to predict that words. Instead, in the next sentence prediction, we split subsequent sequences, and then we say if the two sequences are following each other or not. So we can generate contextualized embeddings, and we will make use of a specific kind of this BERT, which is Alberto. That is a model based, trained specifically for the Italian language, and even more on Twitter messages, which perfectly fit our requirements, since we want to try to classify message like Twitter's, Facebook messages, or even WhatsApp messages. Moreover, we can talk about the hyperparameters tuning, so we can find grid search, which is trying sequentially all the parameters of the model until we find a good combination. But sometimes we miss, as we can see in the image, the good combination. So a random search is basically most preferred. Then we can use a custom genetic algorithm, which I built in order to perfectly match our domain. The genetic algorithm is widely known. What is new in this algorithm is surely the addition of a random individual in order to increase the exploration, and then the fact that this algorithm can also deal with multiple layers as a parameter to tune. Here we finally come to our custom model, which I call the SBERT from the merge of BERT and STEEP, which is the company for which I did this research. This model starts from the input sentence and then is split is fed into 3 different models that are Spicy, Alberto, which I've already seen, and some custom models. From Spicy, we recover the information about dependency relation, name identity recognition, and part-of-speech. Instead, from the custom model, we recover some metadata named like irony, offensiveness, sentiment, and emotion. These information are then downsampled from a series of blocks made of fully connected and dropout, because they are all transformed into a one-hot fashion. And then with the embedding formed by the Alberto model, we can concatenate everything and then make a prediction through a fully connected label. Which is the dataset we use is a post-API dataset, which I get from a manual scraping from its public Facebook page. Then I manually labeled it because all the answers given to the client messages are basically given from frequently asked questions, so I can identify some classes. On the right, we can see the sample distribution among these classes. Then I balanced the dataset, deleting the last class, and then oversampling and undersampling, oversampling with the technique of back translation. And then all the results are then compared with the sentiment task on EMDB dataset. Okay, so those are the results, in which we can find the value of F1 average F1 score. And as is highlighted on this graph, we can see how the effectiveness of TF-EDF decreases as we move towards the word-oriented model, so RNN and LSTM. Instead, the word embed one increases, on the other hand. For what concern instead Alberto and our custom solution, we can see that the additional information we gave to our model contribute for a better results. However, paying the trade-off for a huge and slow preprocessing step and an even slower training phase. That's it. Thanks for your attention.
Thank you. Is any question from the committee?
Just a curiosity, you mentioned a comparison with what was the IDBM dataset?
Yes.
Yes, can you say something about this comparison?
I just searched for all the research with the same, the same combination of TF-EDF and word embedding, and all the models I mentioned, so CNN, RNN, and LSTM, all made on this dataset in order to make this research and this comparison to the values, the results, the best as it can. But
what's the outcome of this comparison? Are your results aligned with the other
Yeah,
results?
sure. The results are all aligned. They vary of 1 or 2 points, but we are there. So we can confirm our results.
Okay, thank you.
Thank you, Professor.
Okay.
I also have a question. So for the word embedding, the only word embedding that you tried are word2vec, right? You didn't try other kind of embedding. Okay, thank you.
No problem.
Okay, is there any further question? Okay, so thank you. So we will ask Luigi Faticoso to connect, to share the screen, please.
Yes, sure. Yeah. Okay, can you see my presentation?
Yes, we do.
All right, perfect. Can I start?
Yes, please.
Okay, perfect. Okay, hi everyone, I'm Luigi Faticoso, and what I'm about to present is my thesis work done for the conclusion of my course in artificial intelligence and robotics. So the thesis work is deep neural network for safety equipment detection deployed on edge GPU using Google Coral. I would also like to thank my advisor, Professor Luca Iocchi, and my external advisor, Giovanni Trovini, as this thesis was carried out in combination with the company of Rome, SmartEye. Okay, so the big idea of my work is to improve worker safety. With some data, we can see that the construction site and factories are responsible for a large portion of deaths at works. This may be partly attributed to monitoring the presence and proper use of safety equipment. Well, this thesis aims to design, study, and implement a working object detection solution from the beginning to the inference and the alarm system. The goal is to provide the state-of-the-art detection quality and to learn from the design process, identify and resolve possible bottlenecks in the detection speed, and recognize important factors that contribute to the overall detection quality. Well, the first step of my work consisted in reviewing some solution for improving the safety in the work, and they can be divided in 2 main groups, the wearable solution and the base camera solution. Among the wearable solution, we can find the solution by Barro Torres in 2012, which consists on using some air feed sensors placed on the equipment, but this has some cons. There is costly, because for every equipment you have to buy some air feed sensors, and it's costly because it's a scanner, and it does not allow the verification of the correct use, because you can go through a scanner with an helmet, but with an helmet in head instead of placing it correctly. It does not allow so the verification of the correct use. Instead of between the basic camera solution, we have the classic computer vision, such as histogram oriented gradients and circle transform, and deep learning. Well, for our case, computer vision solutions are a little flexible in a difficult situation. And considering all the factors from the previous slide, we can see that the best approach to use in this case is deep learning. Since the model has to predict on edge without any connection to an external server, the proposed hardware is the edge GPU Google Coral. This can be seen as a project constraint by the SmartEye. So in this case, I'm going to use the single-shot multi-box detector, SSD, in combination with MobileNet V2 as a feature extractor. Now I'm going to talk about real quick about the SSD architecture. SSD is an algorithm introduced in 2019 by Liu et al., and it is based on feed-forward convolutional neural network, and it uses a BGG16 architecture. How does it work? Well, the single shot in the name suggests that it only takes one shot to identify and extract the feature map, with difference to the older models such as faster and faster region-based CNN. Then a convolutional neural network runs on the feature map to predict the classification probability and the bounding boxes for an object. In our case, this convolutional neural network is going to be MobileNet v2. And then SSD learns the offset rather than learning the bounding boxes. So at this point, after explaining the architecture, I will explain the best approach used for this problem. Well, in our case, 4 neural networks will take place. The first one, that given the whole image as input, it will detect the bounding boxes of the worker, as it is possible to see in the figure below. So it is specialized in worker detection. After obtaining the region of interest, so let's say like the blue one in the figure, it is implied a little bit, and the remaining 3 neural network will run on it. So in this case, the helmet detection neural network will take part in 25% top part of the bounding box. Then the safety vest network will take the remaining 75% of the region, and the gloves detection will detect the presence of the gloves in the whole region. Well, one of the most significant challenges of the training is collecting the data for the model. Well, in our case, I've collected around 16,000 images of safety equipment, mostly manual labeled. I've used label image as an annotation tool, that it is a GUI application to create annotation in XML format that is useful for our case. Then I've converted this XML format into TF record, which is a single compressed file that has all the image and annotation data in it. I've used mainly web-mined images, private dataset provided by SmartEye, and some public dataset offered by NAT and WHO. So here is possible to observe some example for the images taken from the dataset. It's notable to see that images are taken from a particular angle to mimic the same feature input to the system. During the annotation process for the training, I have built another annotation tool. So how it works, it is explained in the image. Let me use an example. By taking by taking a dataset of 5,000 images, I firstly annotated 3,000 images and built an intermediate model based on these images. After the training, I will use the same model to obtain new XML notation files for the remaining 40% of the data. By doing so, I would only need to check the bounding boxes of the remaining 2,000 images and check and fix them accordingly and train the final model with all the data, with all the images and with all the XML files. This has made the labeling process incredibly faster. Another important technique that I used for training is transfer learning, which I've transferred the knowledge from a model already trained on 1 million images and used it as a starting point for our model. Then I obviously trained the last layers with my dataset, and this has different advantages. The internal filters of the model are already confident enough with the objects and shapes present in nature, and you need less data and less training time with respect to the training model from scratch, since we are only training the last layers. So at this point, we have the training, we have the model, and the first tests were run on the helmet network. What we found out is that the model was outputting an unusually high number of false positives. This was extremely dangerous in our case, as it's possible to see in the images in the bottom left, it was taking false positive, drawing bounding box around the faces of the workers without wearing an helmet. So after analyzing the whole issues and the pictures, I found out that redrawing the bounding box to contain only the information about the helmet was a way to prevent the neural network to learn the features of the human faces. So it is possible to see from the picture to the right, I've only drawn the bounding box around the helmet. So by removing the features of the faces, it was possible to have an increase in the metrics as seen in the next slide. Is it possible to see with the old approach? So on the left, the recall and the MIP were lower than 0.5 after 200 steps. So with the new approach, with changing the dataset, the recall and the MIP went around 0.8 with the same numbers of steps. So it was a big improvement on our system to make it more safe. So after having the model, now there is the inference part. So for the inference part, I have to introduce the Google Core Edge TPU, which is a Google purpose-built application-specific integrated circuit used to run AI on edge. In combination with the camera, it is the hardware that were used for the problem and provided by SmartEye. It performs very well in our situation because it performs TensorFlow-like model inferencing with low power usage and great speed. Below, there are the images, and those are the boards used for the problem. Before the inference process, I have to introduce the quantization. Quantizing the model means converting all the 32-bit floating point numbers to the nearest 8-bit fixed point numbers. So this 8-bit representation can be less precise, and the inference accuracy of the neural network is not significantly affected. This process made the model 4 times smaller and obtained 3 times faster prediction. In the image below, there is the representation of the whole process of the conversion from the TensorFlow model to the TensorFlow Lite and compile it for the Edge TPU. Well, in this case, there are 2 possibilities, as it is possible to see in the images: the quantization aware training and the post-training quantization. The quantization aware training, it is a quantization used in the training part. So in this case, it uses, so during the training, it adds some layers. It uses fake quantization nodes to the neural network to simulate the effect of 8-bit values during the training. So these techniques requires modification to the network before the initial training. This generally results in higher accuracy. While instead, in the other way, when we already have a model with float 32, in this case, we can use the full integer post-training quantization, which doesn't require any modification to the network, but this conversion needs, it is required that you need to supply a representative dataset. This representative dataset allows the quantization process to measure the dynamic range of activation and inputs, which is critical to find an accurate 8-bit representation of each weight and activation value. So in this case, we used quantization aware training because we already know that we were going to deploy the neural network on the Edge TPU. So in this case, we started with the quantization aware training so that we had higher accuracy. Well, in the next slide, I'm going to show some results, some notable results of the neural network. In this case, we are talking about the helmet neural network, which is possible to see in the images on the right, that it clearly understands when the head and the helmet is present in the picture. And in the picture below, it is possible to see that it understands all the angles of the helmet. So like in this case, and even many colors, many variations. So we're talking about yellow, white, and red helmet. In those 2 pictures of the safety vest, it is possible to see that the neural network can understand even if there are different colors. So in this case, orange and yellow, and even in an angle that is going to be useful for our future inputs. So the one on top, so seen from above to below. While instead for the glows, since there are so many different kinds of glows in so many shapes and colors, I prefer to mainly detect the negative samples. So in this case, the hands, since they are more recognizable. So is it possible to see that it performs well, both indoor and outdoor, and even in the different angles, and even in angles that we're going to need for our problem. Now, in those 2 videos that I took of myself and a colleague, it is possible to see how the neural network performs. This case was using only helmet and jacket detection. And here it's possible to see some negatives. So I remove my helmet, and it's possible to see that it does not detect the helmet. And I remove even my jacket. So talking about the inference speed, it is notable to see that on cloud, the speed is 2000 milliseconds, while instead on the Edge TPU, it is 7 milliseconds. So thanks to the quantization, it's possible to see that the inference is 3 times faster. So conclusion, the presented method, it is a valid alternative solution to detect the safety equipment and improve the safety management of the construction workers at the construction site. So the model clearly understands a high rate of safety equipment, and it has been tested in real life situation and is ready to be commercialized. My solution can also be further extended by using it to detect specific color and shapes variation of equipment by transfer learning from a model. And there are even many other types of equipment that have been not detected, let's say like the boots, and may be included in my solution by setting my model as a starting point. So this is the work that I've done in combination with SmartEye that lasts for 8 months. And yes, so this is my work that sets the conclusion to my my course in artificial intelligence and robotics. Thank you for your attention. And if you have any question.
Okay, thank you. Is there any question from the committee?
Yes, I would have a question. Could you tell us, please, something more about testing? You performed some testing?
Yes, of course. So we performed some testing with our model using the videos from a real factory, but I couldn't show those videos because of privacy concerns. But yes, we tried in many different situation, so during the day and during the evening, and with many different colors that the neural network was not trained on. Let's say we mostly tried with different types of jacket that, like not in this case, but full, like let's say full jacket. So with many different types, and it was performing well. So we had this test, but I couldn't show in the slides because they were private.
Okay, thank you.
Any further question?
I also have a question. So you said that you exploited transfer learning. So what was the original model that you were using? Was a model designed to detect security equipment, or just a model to detect object in picture that then you retrain it on your task? So what was the original model, and what is the difference that you have seen with and without transfer learning if you tested it?
Yes. Okay, so the model I've used was the one provided by TensorFlow, and it is based on dataset ImageNet containing 1 million images and about 90 classes. And yes, I've tried to do a training from scratch and a training using transfer learning. But of course, doing the transfer learning, having the filters inside already trained and for shapes that can be seen in nature, of course, reduced the amount of time for the training time. So it didn't take as much as training from scratch. And it also, I also had the same accuracy. And even with the data, I even needed less data, because like in my case, especially for the gloves and for the jacket, I didn't have much data as the helmet. So in that point, I really needed less data. And so using transfer learning was the best option in that case.
Thank you. Nice work.
Thank you.
Thank you. If there are no further questions, so we can move to Roggiolani Gianmarco. Please invite to share the screen. Thank you. Okay. Please, you can start.
Thank you. I'm Gianmarco Roggiolani, and my thesis is about the developing of an IMU front-end for a position tracking system. During this presentation, I will give a brief explanation of the problem and the sensors that I used, and then I will present the algorithms that I developed and draw some conclusion with the experiments that I run. First of all, a position tracking system is a system able to identify the position and the orientation of a body into the 3D space. This is done usually using data from sensor that make it possible for us to predict the orientation and position in the near future and to correct our prediction through time. This is done usually with a solver, for example, a least square algorithm, which minimizes the error committed by our prediction. In my case, this problem was associated with a factorization graph. The IMU sensor is one of the most used sensors for unmanned vehicles and aircraft because of its small weight and dimension. It is usually equipped with the two different sensors, an accelerometer and a gyroscope. The accelerometer can be seen as a box of piezoelectric material with a ball inside. Whenever we have an acceleration, the ball hits one or more of the walls, producing a current. Obviously, we always have the gravity acceleration that need to be considered when processing the data. The gyroscope can be seen as a fork-like structure with two driving arms and one sensing arm. Whenever we have an angular velocity different from 0, the stator rotates to the sensing arm is not anymore in the equilibrium position, and we can effectively understand the angular velocity of the body. The two main problems of using an IMU sensor are, first of all, that to have a position information, we need to double integrate the acceleration, and this creates an error that increases over time. And the second problem is that IMUs usually have a very high frequency rate, and it would be not efficient for us to use the solver each time we get a new measurement. My first approach was a cumulative one based on the literature, and whenever I had an IMU measure, I would just update the value of the acceleration and angular velocity, and obviously the time. And then I would compute a mean for the acceleration and angular velocity whenever I had a new odometry measure from the aiding sensor. In this way, I could compute the factor using the mean for angular velocity and acceleration as a reference to compute the error, and using the odometry measure to compute an estimation for the velocity. The main problem of this approach is that we lose a lot of information of the acceleration and angular velocity between the two odometry measures, because we are flattening to the mean value. That's why I tried with a different approach, a more refined one that I call the chain approach, where basically I computed a factor every time I had a new measure that it was from the IMU or from the odometry sensor. Obviously, the main problem here is that using the IMU measure to compute the next estimation means that we will have a factor with 0 error. That will not really help the solution, but it is anyway corrected with a backpropagation when I have the big error coming from the odometer measure. That's why the chain approach was a good solution, because it linked all the position through time in an easy way, even to compute for me, and it would help the estimation through time of the trajectory. The factor that I used needed obviously the access to the poses, so position and orientation, the velocities, and acceleration, angular velocity, and the difference in time between the two poses. I also did some experiments with the possibility to estimate the bias. And having this information, it's easy to compute a prediction of the new position, angular velocity, and acceleration, which is straightforward from the rotation and velocity of the previous time, using the difference of the rotation over time or the difference of the velocity over time. In this way, I could compute three-dimensional error in position and angular velocity and acceleration, and the Jacobian needed from the least square solver to fill the Hessian matrix. So the Jacobians are just the derivative of the error with respect to the different variables. I did several experiments trying to understand which was the best approach and which variables and parameters could make a difference. In this case, we're seeing the cumulative approach, so the first one that I presented with the two different odometry frequency. What we can see is that even if both the results are not perfect, in the first case, the result in blue is not really spiky, but it's a lot worse than the result with the higher odometry frequency, where we can say that having more measure help us trying to help the solver to constrict, we can say, the result towards the ground truth, even if the result is not smooth as the one before. This made me realize that higher odometry frequency had obviously a better estimation for the final results. So I tried with another trajectory, and I made a comparison between the cumulative approach and the chain approach. That are on the left and on the right. This second trajectory had 0 x coordinate and was mainly moving on the plane, as we can see. And I also introduced a theoretical enhancement that was the fixed lag smoothing that should help the estimation in these loops where the body was passing through the loops 3 times before moving out. What we can see is that on the x coordinate, the chain approach outperformed the previous one. We see that the maximum error goes from 1 to 0.2. And on the plane, we can see that the fixed lag smoothing is working a lot better on the chain approach, even if we have some errors here that is not really visible here. This is mainly caused by the chain that we created. So the error that was discovered in the loop was back trajectoried. But anyway, the final results are a lot better in the chain approach. That's why I focused on that one. And I, in this slide, we can see I used other 2 enhancements from theory, well known. The first one is the spherical linear interpolation on the left, where basically I try to increase, we can say, the error even in those vectors where the error was 0. In order to do so, I weighted the second measure from the odometry sensor, and I used the spherical linear interpolation to estimate the angular velocity without using the one from the IMU sensor. And in the last experiment, I introduced the bias estimation. What we can see is that in the final one, the trajectory on the plane is almost perfect. And anyway, on the x coordinate, we reduce ulteriorly the error that is now 0.1, maybe something more, but anyway, it's still very little. I did further experiment to really understand how the problem was formed. The first thing that I did was try to increase the noise on the odometry sensor. Obviously, the final trajectory is a lot worse, as we can see, both on the plane than on the x coordinate. But what I found interesting is that making a plot between the data with the noise injected and the resulting the result of the solver, the error was almost 0. This means that the problem is most probably not is underdefined, and so the solver is not really able to understand how much the noise is affecting the trajectory and can just reconstruct the data that we gave you. Other experiments that I did were on the threshold, for example, for the fixed lag smoothing. The most important thing for me to see in this case is that we need to make a compromise between the performance and the complexity of the problem. Obviously, increasing, as we can see in the lower picture, increasing the threshold means that we have a smoother results in blue. And it's almost perfect, but obviously this also means that the dimension of the problem is a lot bigger and we need more time to compute it. The 2 tables in the slide are like a qualitative comparison of the different approach. As we can see from the cumulative to the chain approach, we have a big leap in the performance. We have a big difference, and every time I used a new enhancement from theory, the maximum error was reduced. This also means that we need more time. Basically, this is due to the fact that every enhancement needed, or in the case of the spherical linear interpolation, we needed to wait the new odometry measure. But in all the other cases, we are adding variables and factors to the problem, which becomes bigger. And this obviously means that the solver needs more time to solve it. But anyway, the longest run that I had was 1.5 minutes to solve the whole trajectory in just one batch. So I didn't use the solver every time I had a new measurement. So these are my conclusions. I presented a way to use the solver just once and to achieve good performance. What I could add to this work, there are several things. For example, we could add some prior knowledge. In the case of my second trajectory, if I fix the x coordinate to be 0, for example, the dimensionality of the problem would be reduced, and this would lead to a better estimation for all the other variables. We could add a Coriolis effect and centrifugal force to have a better estimation, especially when we are talking about the trajectory of drones. The estimation of threshold that I did using, we can say, trial and error could be done using a deep AI or using the parameter as variable of the problem. Other two things are the possible use of the magnetometer data from the IMUs, because some of them have this other information. And obviously, if we are adding a new sensor, means that we have more information to solve the problem efficiently. And the last thing was just an idea that I had, because working with the code, you usually have a lot of problems when you have to modify the code from someone else, and it's tedious to change all the variables every time you have to run an experiment. So having a command line problem configuration would be really nice. And thank you for your attention, and I'm here for any questions.
Thank you. Is there any question from the committee?
Just a curiosity, where the data that you use for the experiment come from?
Okay, the trajectory, I created them from 0, and then I injected the noise each time when I ran the experiment. I also tried with the real data, and so I don't have the plots here. The results in terms of error were almost the same, so I think that the performance were basically
just the second curiosity. In the case of real data, how did you get the ground truth?
It was a data set that I downloaded, so they had the real data that they gave both the real data and both the noisy one. So it was like one of the things that they gave, and it was why I used that data, because obviously there were no other possibilities to effectively see if the algorithm was working or not.
Okay, thank you.
Any further question from the committee?
I have one.
Yes, please.
Hi, Gianmarco. I mean, I'm just curious that about the whether there is room for some further optimization, like meaning in the end, the bottleneck from the computational point of view is like this, the solution of the linear system, right? The H matrix. Isn't there any special structure that we could use, like to if it always has the same shape, the same filling pattern, one could pre-solve it or pre-compute an ordering. Did you observe any recurrent structure in the H matrix?
Okay, I do not really like so I did not really print it the value. But, what?
by feeling.
Yeah, but obviously, like the final structure is has like a full diagonal because we have all the information from like one step to the previous one, obviously because of the odometry and the IMU data. And obviously there are some other points in which we have information that are like symmetric when we have the fixed lag smoothing, for example, because we are just saying that two positions are the same. So we have further information in those spaces. So like we could use sparse optimization.
I see.
Okay.
Okay, thank you.
Okay, if there are no further questions, we interrupt the session. The committee will meet on the other room. So I wonder, I said before that we will meet again for the second session at 11:30, but take into account that we were quite fast. I propose to meet at 11 if there is no objection about that.
No objection.
Okay. So now we proceed as follows. Now the committee will meet, and then as soon as we have complete our evaluation work, we will come back to this room for the final proclamation of the students. And then, so we expect that it will take about 20 minutes, I would say. So more or less, depending on it's not always predictable. Okay, so the committee move to the other, and please remember to disconnect audio and video from this meet room. So disconnect the
da 107. Attenzione, attenzione, c'è il microfono aperto.
Non sento più nessuno.
Bene. Okay, so just to see we are everybody. So I want to be sure that the students are Faricelli, Faticoso, Raggioni. I do not see the Faricelli. Sorry, just to Faticoso. I don't see Roggiolani. Ah, yes, here it is. Sorry, I didn't see it. Okay, the following students have passed today the graduation exams in artificial intelligence and robotics with the following grades. Faricelli Simone, 107, 107. Panticoso Luigi, 110 cum laude. Roggiolani Gianmarco, 110 cum laude. On behalf of the Rector of Sapienza University of Rome, I confer them the Master Degree in Artificial Intelligence and Robotics with the congratulation, my congratulation and the congratulation of all the committee. Good luck for your future life. Congratulations.
Thank you.
So I'm very happy. And I wish you all the best, and you keep a good memory of these years. We will meet again for the second part at 11 sharp. So just to fix, and then so we have a break. So at 11 we will continue with the second part of this committee for the graduation in computer engineering. Congratulations again, and see you soon.
Thank you.
Ok. Allora, a questo punto io mi sento da 8 microfoni, ragazzi.
Ecco, siamo rientrati.
No, attenzione, Marchetti ha aperto il microfono.
No, ma non siamo su Zoom, siamo su Meet. Siamo su Meet o su Zoom?
Adesso eravamo io e Giuseppe su Meet perché stavo precompilando i verbali. C'è questo Marchetti che è il microfono aperto su.
Questo mi sembra che sia su Zoom, Alberto.
Adesso sei su Zoom. Zoom non è mai stato su Zoom. Ah, ok, io sto facendo casini su questo. Senta, io sono il seduto di laurea, ci possiamo sentire tra un paio di ore. Grazie. Ok. Allora, io confondevo su quale video. Chiudete tutti i microfoni sul Meet. Allora, lasciamo Meet.
Okay, so we start again.
We are on Zoom, Alberto. Yeah. We are on Zoom because
yes.
Zoom is connected to the streaming.
Yeah, I'm on Zoom as well. So we should start before you, Giorgio. You should switch off the video recording. So now we are. No, we can. We have already identified all the students, right? So we can start. So we now start with. Sorry.
I never switched off the video recording.
Okay.
The video recording, because otherwise it changes lineage.
Okay. Okay. So we are starting now with the final exams for engineering computer science. So first student will be Abruzzo Giuliano, that I invite to share the screen and start his presentation. Okay.
Okay, can you see the screen?
Yes, we do.
Okay. One moment. Okay, today I'm going to present BIB Identifier, a platform for classifying photos of sports events. This is a platform that was made during an internship in a company called Advent, together in a group with other two students, Federico Gioia and Francesco Carpinetti. The goal of this thesis is to develop a web and mobile platform capable of labeling marathon pictures uploaded by the photographers with respect to the BIP numbers appearing in them. The machine learning algorithm will process all the photos uploaded by the photographers, and the standard user can search the events by the name of the events and can filter the related photos by the BIP number. You can also report error to the photographer user, which is able to manually correct the labeling errors. The users will directly interact with the web and mobile front-end, and the web server made in Flask will handle every other component of the platform. The storage, the user management, and the database were implemented through Firebase. The storage is used in order to collect all the photos of the sporting events. Instead, the database will contain all the details of the events, but also the big numbers related to the photos and the data of the users. I mainly contributed to the platform machine learning algorithm. This is composed by three main stages. The graph stage, in which we localize, identify the text areas present in the photos. The box processing stage, in which we apply a sequence of transformation and operation. And then we have the tesseract stage, in which the tesseract OCR engine is applied, and then the results are inserted into the database. CRAFT, or Character Region Awareness for Text Detection, is a text detection method that finds text area by exploring each character and the affinity between characters. This is a convolutional neural network based on VGG16 with batch normalization, and it produces two outputs, the character region score and the affinity score. The character region score is used in order to localize character inside the image, and the affinity score instead is used in order to group this character into an instance. And so Craft can be used both in word-based mode and in character mode. For our project, we use the official implementation of Craft present in GitHub, available to PyTorch, and in word mode. And we can see that from a starting image, Craft will found all the boxes present, all the text area present in the image. Then we are going to apply some filters based on the dimension of the bibs number, since we can imagine that in marathons the bibs are wider than they are high, and then based on the size of the box compared to the size of the image. Then the boxes are finally cropped and rotated. Then we have the box processing stage, in which each box found is converted to grayscale and is doubled inside. Then we are going to apply some different kind of operation on it, like different binary threshold from 140 to 190, but also opening operation in order to remove noise, and inverted colors, since we don't know in advance which color the bib numbers will be. And also an operation of the equalization of the histogram. That is an operation that improves the contrast in an image. And we can see from this image that in this case, thanks to the operation, the bibs that are with the reflection of the sun on it can be computed correctly. And in total, we are going to generate 48 different versions of the original box. These boxes start and then pass to the Tesseract OCR. Tesseract OCR is a OCR engine sponsored by Google, and is it possible to Tesseract to whitelist only some characters? In our case, we tried to whitelist only the digits, but we saw that Tesseract will try to guess numbers even from text boxes that doesn't contain at all any digits. So we discard this option, and we filter the output of Tesseract in order to check if the result is a digit and it contains at least 3 characters. Then we are going to select the bib numbers with the most occurrences as a result. And this result is then inserted into the database. And these operations are performed in parallel using the Python and Futurals module. In order to evaluate this algorithm, we use two different kinds of datasets, the U-Bally dataset and the RMBNR dataset. The first one is composed of 40,800 photos, but the company has selected only 1164 photos, which have been classified manually in a CSV file, where each photo is associated with the bibs present in it. And then we have an RMBNR dataset composed of 200 images of different marathons. And unlike the previous dataset, the bibs here have text with different colors, and it also contains images with much lower resolution, as you can see from the tables. We used 3 kinds of metrics, the precision, the recall, and the NED. The precision is the number of correct results found divided by the number of all returned results. The recall is the number of correct results found divided by the number of results that should have been returned. And then we have the NED, that is the lowest distance between the 2 strings divided by the length of the longest one. And in order to match the bib found and the correct bibs, we use the Hungarian algorithm, which allows us to associate those with the smaller lowest distance. The lowest distance, also called David distance, is the number of substitution, edit, insertion, or deletion in order to change a word into another. And this NED will be a value between 0 and 1. The evaluation were conducted both on the algorithm with the filters on the box found as described in the graphed slide, but also to the counterparts where the filter on the dimension are not applied, and all the boxes are analyzed by the tesseract OCR engine. We inserted in the tables 2 different values of the NED. The first one represents the computation of the NED only for the subset of the BIP found, and the second one is the NED also for the BIPs present in the ground truth but not in the result. And we saw that in the version with the filters, the precision is higher. We have 8% plus of the precision, but the recall dropped by 22%. So this means that a lot of correct text boxes are discarded by the filters. Then we have the NED that passed from a 0.2 to the 0.1, so the algorithm is more accurate. And we can see that the filtered box represent 1/3 of the total boxes. This means that we save a lot of times and a lot of computational power thanks to these filters. We also evaluate if the use of the resize and the opening function for the box lead to benefits for the algorithm. And we saw that in the version without the filters, the resize operation and the opening operation leads to an increase in both precision and recall for about 2-3%. And instead, in the version without the filters, the results are practically the same. And we also used a subset of 100 photos that are blurred or with the reflection of the sun in order to evaluate if the use of the histogram equalization operation is useful or not. And we saw that the recall is increased by a lot. In the version without the filter, we have a recall that increased by 20%, and in the version with the filters, 11%. Then we have the evaluation on RMB and R dataset that is much smaller than the previous one. And we have lower result compared to the previous dataset. This is caused mainly by the fact that the photos of this dataset are a very low resolution, and this does not allow correct analysis of the BIPs. And both the operation of resize opening leads to worse performance respect to the normal version. In conclusion, BIP identifier is a good starting point when trying to implement a platform that helps people to find their picture by the BIPs, and it also saves times that will be wasted in labeling the picture manually. Right now it's limited to marathon picture and numerics BIPs, but it can be extended to every kind of event where an alphanumeric code appears in a picture as an ID. And the machine learning algorithm does not guarantee good result for low resolution images, so we could implement a system that disables the opening function in case of small images. But we can also realize a system of recognition of people bodies. So in such a way, we can discard all the non-useful boxes inside the image. And lastly, we could evaluate the possibility of using craft in character mode. So selecting the BIP character one by one, and then based on their position, recombine the number together in order to evaluate if this mode provides a better result than the word-based one. Thanks.
Thank you. Is any question from the committee?
Yes, I have one. I see this problem quite similar, for example, to car plate detection and recognition. What, I mean, is it different? Did you try techniques that have been developed for car plate?
Yes, we also check another number car recognition paper, and we saw that they used another method that is I don't remember the name, sorry. But with this method, they used in such a way that they can recognize the car plates by number by one, practically. But yes, it's practically the same.
Okay, so maybe a comparison between approaches that have been developed for car plate recognition may be useful to understand, for example.
Yeah, okay, we didn't do that, but
okay.
Yes.
Thank you.
Thank you. Is there any further question? So I have a question. Would you say in perspective, what could be some application of these, in the sense that only for people to find their own pictures in some stream, or there could be some other
For now, it's just a research and develop project for the company, but the goal of this platform is continue to improve until this can be sold to every kind of customer. So in a marathon or in sporting events in general, like you can imagine bot racing or something like that.
So it's the goal is to keep, I mean, in the sport, so to check whether nobody took a shortcut, for example.
Yeah, for example.
Okay. So, and there are no, I mean, according to you, I'm not saying it for your project, but in perspective, there could be any other application of these kind of things, because clearly there is the limitation of the digital identifier somehow. So in this.
Yeah, we didn't think about it, but it's about the company. The company should decide what to do with this.
Okay.
Thanks.
Okay. Is there any further question? Okay. So thank you. And I kindly ask Trapasso Alessandro to share the screen.
Yes. Do you see me?
Yes. Yes, we do.
Good morning. My name is Alessandro Trapasso. The name of my thesis is Multi-UAB Reinforcement Learning with Temporal and Priority Goals. The Bubble project inspired my thesis work. It's a project funded by the European community. And the main goal is to define use space that allow the use of drones safely and efficiently. To do this, AI algorithms are used to calculate and minimize the risk of collision between UAVs. The focus of the Sapienza unit is to implement a method to generate many trajectories for risk assessment. The scenario of my case study was inspired by an operational case of the Bubble project. In this scenario, there are N UAVs and K hospitals. Each agent must take the resource from a specific hospital and deliver it to the hospital that requests it. UAVs must visit the hospital in a given order and must respect the mission priority assigned to them. The concept of priority is important. The European community has already defined this concept in a document. Another main goal is to reduce to zero, or in any case, minimize the risk, the possible collision between UAV. The objective of the abstract problem are find an optimal policy for each agent, reducing interference between agent policy. Agents must respect the mission priority associated with each goal and reach the goals in the correct order. Before defining a problem, we need to make assumptions. We assume that there is a global clock that marks the time of each agent. Goals are asynchronous, so any agent can start the mission at any time. Each agent doesn't know the position of other agents. Now let's define the problem. We have a scenario S. S is a tuple that contains the set of agents. Each agent is modeled by an MDP problem, and restraining bolt and RB is the set of restraining bolt. Calligraphic M contains the MDP associated with each agent. Each MDP is a tuple of set of state, set of action, transition function, reward function, and discount. Gamma is the discount factor ranging from 0 to 1. Restraining bolt is a specification represented in temporal logic to establish the order between the goals. The behavior of each agent is learned through the use of reinforcement learning and Restaining Bolt. Restaining Bolt was introduced in 2019 by the Giacomo et al. This thesis work extends the original Restaining Bolt by adding the concept of priority. Each Restaining Bolt is a tuple that contains calligraphic L is the set of fluids. In case study is the color assigned to hospitals. Each reagent has a goal phi A, PA, where phi A is the linear temporal logic or linear dynamic logic on finite trace formula that the agent must satisfy. PA is a non-negative integer associated with this formula to indicate priority. R is the reward associated with the goal, PA. In the reinforcement learning, the agent performs an action and receive a reward and observation from the environment. With the bolt, the agents receive two independent rewards, one from the MDP for each state action, and another from the Restaining Bolt based on the state of the automata. We face a multi-agent reinforcement learning problem with independent learners. In this type of problem, if agents don't exchange information with each other, it is impossible to find an optimal policy for each agent. To obtain an optimal policy for each agent, the system should be centralized. In the solution of a case study, we show how it's possible to find an optimal policy concerning the concept of priority through independent learning. In our solution, we find n policy, one for each agent. Each policy is optimal and satisfies the agent's goal. In the case of conflicts between agents, the conflict is resolved in favor of the agent with high priority. To reduce the interference, we define for each agent a new function called the no-interference reward. Let's imagine we have n agents. Each agent has priority p, ranging from 0 to n-1. We sort agents by priority. The first iterated agent has always the highest priority p equal 0. So its no interference reward equal to reward function. For other agents, the no interference reward function is the sum of the agent's reward function with the trajectory generated by the execution of the previous agent policy. Now we replace the reward function in the MDP with the no interference reward function. We find the optimal policy using the reinforcement learning with Restaining Bolt augmented by executing the optimal policy. We obtain the trajectory that we will use in the next iteration to calculate new no-interference reward. The case study is a model of our hospital problem in which the world is represented in a grid. And the Restaining Bolt gives a positive reward if the agent does hovering in the right order on the cell of the hospitals. In our case, the no-interference reward has been implemented by adding negative weight on the cell crossed by the trajectory of the previous agents. The temporal goal formula specify the emission of each words and the temporal order of the goals. Now I want to show you some of the experiments we have done. The reinforcement learning algorithm used for the experiment is SARSA, state action, reward, state action. but we should use also other algorithm, other reinforcement learning algorithm. As we can see in experiment 3 without priority, the trajectory of the UFV intersect with each other. In experiment 4, we resolve this conflict with priority and with our non-interference word function. The purple UFV has the highest priority, so its trajectory is the same in both experiments. The orange UFV has priority 1 and the gray UFV has priority 2. It's possible to perform experiment by increasing the size of the map, the number of goals and agents. Our system is scalable, and we can generate address of trajectory at lower cost. That a standard multi-agent algorithm, in which case the cost will be exponential. Our methods find an optimal policy for each agent, reducing interference between agent policy. From the execution of the policy, we generate trajectory with a lower frequency of conflicts. In a possible future work, we may analyze the case in which the UFVs depart in a predetermined time interval. Use the no-interference word that we have described in another possible scenario, and also integrate this solution into bubble to minimize the risk of UFV conflicts. Thank you for your attention.
Thank you. Is there any question from the committee?
I have a question. So
please.
At some point you mentioned something that is a centralized coordination. So I didn't understand then exactly where there is this centralized coordination, if I understood correctly, and why you need the centralization. So could you a bit explain more about this?
Yes, because when the multi-agent algorithm, multi-reinforcement learning algorithm is centralized, the state of the agent is shared with the cost augment in exponential. But in our case, the system is scalable, and the agent, the cost of the algorithm is lower of the respect to the multi-agent reinforcement learning algorithm with centralized.
Okay, so centralized means that each agent can see the state of each other.
Yes.
Essentially.
Yes.
Okay.
Yes.
In your approach, this is not true, so it's fully distributed. Okay.
Yes.
Okay, thank you.
You're welcome.
Is there any further question? So I have a question. I wonder whether there could be some, I'm not an expert in the area, but I have the feeling that there could be some situation in which might be some sort of deadlock among competing or not, or this is avoided in the sense that competing requests that are arriving, in the sense that deadlock, in the sense that some vehicle might be blocked by repeatedly block or have to change dynamically the route.
Yes, on each agent is find your optimal policy, and by the execution of the optimal policy generate the trajectory.
This is not to change after new information is available.
No, it's a predetermined trajectory.
So this influence, so that's required to be communicated to everybody.
Yes, it is scalable with each agent. Is have state and our state action, and is separated each other.
Okay, thank you. Is there any further question? Okay, so thanks, Abruzzo. We ask Trapasso Alessandro to share the screen.
I think it's me. Trapasso is the guy who just.
Oh, sorry.
Presented.
I apologize. Sorry, I'm.
You're welcome.
Brenta Valerio, please.
Okay.
Sorry.
Can you see my screen?
Yes. Yes, we do.
Okay. So good morning. My name is Valerio Brenta, and I'm going to introduce this work in which we investigated the use of control flow graphs and natural language processing in order to automatically name binary functions. So the targeted problem often arises when performing a reverse engineering activity on a binary sample. The manual approach is usually that of reversing with the help of a disassembler tool. However, this is a very challenging approach because the human expert has to go through a series of assembly instructions, which is a low-level language and very hard for human to understand. And this also implies that this approach is time-consuming. To define the function naming problem, given a binary piece of code or function, we aim at mapping this function to a meaningful set of words so that these words would compose the name that an expert would assign to the function to describe its behavior. Why do we need an automatic solution? Because reverse engineering problems in general require a lot of time, and they are often carried out on a malware analysis context. And we have seen, witnessed during the last decade, an exponential growth of the total number of malware infections. So to tackle all of these infections, we need to have more and more manpower, and the manpower request obviously leads to increasing costs, especially for enterprises. NLP techniques may provide a solution to the function naming problem. Indeed, in the past few years, these techniques and machine learning models have been investigated by several works, which we're going to see in the next slide, on all kinds of engineering problems, software engineering problems. They all share a common starting point, which is the naturalness hypothesis, in which the authors, Almanis et al., regard software corpora as corpora having similar statistical properties with respect to natural language corpora. Regarding the state of the art, the works that we gathered can be mainly divided into two categories: works on source code and works on binary code, with the former actually achieving much better performance as usually. With respect to this thesis, it falls under the category of binary code works, in particular approaching the function naming problem and doing it by leveraging an assembly-only source domain. So the challenges when dealing with assembly language are mainly three, the ones that we address. The first one is the long-distance dependencies, meaning that we are going to represent functions as sequences of instructions, and these sequences are actually very long and much longer than natural sentences. Furthermore, obviously, we need to grasp the instructions context, since a single assembly instruction is usually less self-explanatory than a single human word. And moreover, we might also have noisy operands to the instructions, such as memory-based addresses or registers, which may further confuse the prediction system. So our approach consists, first of all, in extracting execution paths from the control flow graph of a function, which is defined as a directed graph, having nodes as basic blocks holding the assembly instructions and connected through link through directed edges. We also retrieve statically defined data from our functions. So for example, strings that may have been introduced by the programmer when writing the code. And finally, we perform normalization techniques, for example, by normalizing the registers into different categories depending on the data they hold and their word size. An execution path is then defined as a sequence of instructions that are traversed or met during a single execution of a function. For example, the sequence of instructions contained in basic blocks A, B, D. During our tests, we also evaluate whether the order of the instructions can affect the predictions. When building our dataset, we do it from scratch, and we mine from the Ubuntu official repository over 2 million of functions. For each of these functions, through the Ghidra disassembler, we retrieve their control flow graph, and then the execution paths by performing random walks on these graphs. We also retrieve a set of general function information that we do not exploit in our experiments, but might be useful for future works, such as, for example, the compiled code that we get from Ghidra. This is a very high-level overview of the architecture that we exploit, that is the transformer, state-of-the-art model in order to solve neural machine translation problems. In particular, in our case, here we are feeding an execution path as an input and getting as output the name of the function it belongs to. The transformer follows the encoder-decoder paradigm, in which both encoder and decoder are composed of a stack of n layers, one on top of another, so that the output of one layer is the input to the next one. The first approach that we test is the transformer with majority voting. Through this method, we actually feed to the transformer separate execution paths composing each function. And for each of these execution paths, we retrieve the name that is predicted by the transformer, that is the name of the function the execution path belongs to. Then at this point, we group all of the predicted names by function, and through a majority voting system on the tokens of the function names, we predict the final function name. We also test a second approach, that is the transformer with sets of execution paths. In this case, this architecture is slightly different because we provide as input an entire set of execution paths which represents a single function. So we are providing, in this case, k execution paths as a set, and each of these paths is embedded through the embedding layer of the transformer, which is fully trainable, so that each token of the execution path is represented as a single fixed size vector. Then we perform pooling in order to downsample and retrieve for each of the k execution paths a fixed size vector. We test two different pooling strategies, either attention or average pooling, simple average pooling. And we also evaluate whether the component that is the positional encoder of the transformer may actually affect the results that we get. So with respect to the majority voting approach, we gather the predictions and compute the results on metrics of precision, recall, and F1 score. And what we can see is that the transformer can actually learn some patterns in the input paths. However, these scores are not improved with respect to previous works. We also see that there is little difference in terms of results when comparing the scores on randomly ordered instructions in basic blocks and address ordered instructions. This very same result can also be observed when looking at the results of the sets of execution paths approach. These scores are actually lower. Nonetheless, they're still interesting because, first of all, we can see that there is little difference when comparing average with attention pooling. However, in both cases, attention pooling leads to a slight improvement in performance. Moreover, what is interesting is that by including the positional encoding component on the transformer, we actually get worse outcomes. This is to be expected, actually, because we are feeding as input a set of execution paths as a function, but the position that each execution path covers in this set is actually meaningless because we are retrieving these execution paths through a random walk, so through a random process. We also performed a third final experiment on a BERT architecture. BERT is basically a transformer, but only leverages the encoder component, so without decoder, in order to also perform a kind of learning that is self-supervised. So we pre-train this BERT architecture in order to check how it performs on an input that is randomly shuffled instructions in basic blocks for each execution path. And we check it on the masked language modeling objective, which is specifically at the token level, so that, for example, we randomly mask off some of the tokens inside the input paths, and we train BERT on correctly guessing the tokens that have been removed from the path. And what we can see is that, surprisingly enough, BERT can actually achieve an accuracy score on the mask of tokens that is much higher than the one achieved by a random prediction system. In conclusion, we have seen that it is possible to model the function naming problem with execution paths and NLP techniques. However, the proposed architectures, as well as the techniques we have applied, do not provide any advantage with respect to previous works. But we have also seen that with the sets of execution paths, the positional encoding component is actually leading towards performances, and that the instructions order inside each basic block is actually not relevant with respect to the architectures that we tested. As future works, we would like to check on improvements on both majority voting and sets of execution paths approach. In particular, with respect to sets of execution path approach, we might leverage a transformer encoder to actually embed each of the execution paths, or even leverage the pre-trained embeddings that we might get from the BERT architecture. We would also like to evaluate the impact on performances of the basic blocks order when building the execution paths. And finally, an alternative solution would be that of exploiting different features or higher level representations in order to represent these input functions, such as, for example, the decompiled code that we retrieved in our dataset through Ghidra, as it is detailed in other works to lead to improvements in performances. That concludes the presentation, and thank you all for the attention.
Thank you. Is there any question from the committee?
Hi, I have one question actually. Concerning the second architecture you showed.
Yes.
I've not understood the executions path, they can have different length, or are they of a fixed length?
No. They have all the same length. We have padded or truncated the execution paths to the same length.
So when you do pooling, you're doing pooling at the level of a single instruction?
Yes.
Okay. But then how can you, I mean, are you always sure that these are comparable, let's say?
I'm not sure I have understood. I'm sorry.
I mean, if you are, for example, at step 4, for example, of the path, and you do pooling, you are assuming that the steps in all the sequences are somehow comparable.
Okay, I think we pull only after we have retrieved all the embeddings. Okay, so we have basically a set of K execution paths, okay, and they are represented as after the embedding as a matrix of rows that corresponds to the number of tokens and the columns that correspond to the embedding size, obviously. And then what we do is that, for example, in the case of average pooling, is just to compute an average between all the vectors of the tokens. So to retrieve a single fixed size vector.
But then the input to the following part is not a set or a sequence anymore, right?
It is a set of K vectors.
Oh, of the K vectors. Okay.
Yes,
now I understand.
Yes. Okay. Of the K vectors that are representing each execution path.
But in this case, does it make sense to have positional encoding?
Exactly. That's what we wanted to test with our results, because this is not a sequence, obviously. And so we are performing positional encoding on the set of the execution paths, not on the tokens, okay? And what we retrieve during the random walk are execution paths in a set, but obviously they do not follow an order in this set. So actually, when adding positional encoding, we get worse results because we are just adding noise, basically. So yes, it is better without positional encoding.
Okay, thank you.
You're welcome.
Thank you. Any further question from the... Okay, so if there are no other questions,
stop.
Thank the speaker, and we are going to meet. The committee, we should close video and audio on this, on the Meet, on the Zoom, and then we should move to the Meet room. Sì, qualcuno mi ha spinto l'audio.
C'è il microfono su.
Okay. Okay. Welcome. Okay. We are ready for the final declaration. So the following students have passed today the accreditation exam with the specified grades. Abruzzo Giuliano, 103. Trapasso Alessandro, 110. Trenta Valerio, 110 cum laude. On behalf of the rectress of Sapienza University of Rome, I confer to them the master degree in engineering computer science, with the congratulation of my congratulation and the congratulation of all the committee. Congratulations. So good luck for your new life, and I hope you keep good memories of these years. Congratulations again.
Thank you. Bravi.
Thank you.
Bye. So the session is closed, and then I wish you a good summer. Bye. Good Easter first.
Thank you. Goodbye.